Okay, so this is a video about moments of inertia as a topic of CIE further mathematics A-level, the mechanics section. I've already done some videos on rigid bodies in equilibrium and on simple harmonic motion, and I'm probably will be assuming knowledge of the other topics in this video. In particular, I'm assuming you already know about how to set up the equations of motion for simple harmonic motion and how to use simple harmonic motion as an approximation. It's not the main point in the video, but it is assumed. Right, so moments of inertia. We should start by reviewing the basic concept. What is the idea of a moment of inertia? I'm going to show you some notes and just make a few brief points. And then I'm going to talk briefly about how we go about finding moments of inertia. And then I'll straight away dive into some examples, two exam questions in particular, from I think 2010 and 2004. Just fairly typical examples of what the examiner will be asking you to do with moments of inertia. So let's review the basic concept by means of looking at a couple of notes, if I can pull it up. Yeah, so this page, as you can probably see, is a website that we set up in our school. Well, it's mostly me that did it, called SCIE mathematics.wikispaces.com. And this site hasn't been updated actually for at least a year, I think, so you may find some old stuff there that's not, well, in fact you'll definitely find a lot of things there if you go to that website that are not relevant. You don't have to log in as a user of Wikispaces to look at the website, so don't worry about that. On this page I put a bunch of stuff basically about further mechanics, and I've actually already linked some of my other videos there, as you can see. I've written a sequence of topics, and that's not why this is interesting. The only reason this is interesting is because there's a bunch of notes here which are intended as very concise revision notes. Now, I don't know how easy people would find this as a revision resource. Especially if English is not your native language, some of this text might be a bit heavy to read, but that's because I've tried to be very, very exact and concise and give you advice exactly what to do in different situations. These are the notes about rigid bodies. Then there's a large set of notes about what I've called rotational dynamics. So I'm summarizing here all the knowledge you need about starting with motion in a circle, and as you should already know, we use motion in a horizontal circle and in a vertical circle, much more complicated case where the acceleration can vary. So this little section here reviews the basics of angular velocity, angular acceleration. I mean, the main equations to know are v equals r theta dot, meaning the linear velocity is equal to the angular velocity times the radius, and theta double dot here, so this dot notation meaning derivatives with respect to time, theta double dot being the angular acceleration, being the second derivative of angle, or theta, with respect to time. As you can see, sometimes it's written alpha, but usually not. So this might all definitely be worth reviewing if you don't know it. But today we're focusing on the concept written here as I, or moment of inertia. So what is moment of inertia? So that section starts here. The main concept is to think that just as we have mass to describe the property of a body which resists changes in acceleration. So your physics teacher will tell you, strictly speaking, that concept is the concept of inertia. And it just so happens that mass is the property of a body which gives it inertia. So for every kilogram of mass that a body has, it has one extra unit, so to speak, of resistance to change in its motion. And change in its motion means change in its velocity vector. And change in a velocity vector is written as acceleration. So you've learnt how to do that in the case of motion in a straight line, and you might even have been able to apply the idea of acceleration to motion in not a straight line. Not only circular motion, for which you almost certainly already know this formula A equals v squared over r. Where is it? Up here somewhere. A equals v squared over r, AC being the centripetal acceleration, which can also be written as r theta dot squared by using this substitution. So you know the idea that acceleration is not necessarily about something moving in a straight line. It can also be used at any one moment to describe what's happening to a body moving along a curve. Obviously that's more complicated. But here we're focused completely on situations in which an object rotates around a single point. So maybe before I say anything else I should mention that that we're talking about, if I could just illustrate, a particular point as a center, sometimes called a pivot, of course, and then a body, and you know the shape of the body may be variable, but the body rotates around that center. And if the body is rigid, that means its shape does not change. That gives us a very special and useful fact, which is that each that's not very good. Each part of the body rotates. Okay, these circles have different radii, so you know R1 and R2. Imagine they're circles. I know they're not, but you know it's just drawing. So the point is that every particle in the body is rotating in a circular motion around that central point. But whilst the speeds of the particles, so this, you could imagine this is P1 here, one particle in the body, and this is P2, another particle. The speeds of the two particles will be different, won't they? Because the ones closer to the centre have less distance to travel, so they'll be going more slowly, whereas the particles further away will be travelling more quickly. So they have different speeds, but what they have in common is they have the same angular speed. And that's why an analysis of this situation using angular speed turns out to be much simpler than an analysis using velocity or speed. So what we're doing here is trying to shift all the equations of motion, F equals ma being the main one, shift all of them into an angular form so that we can write something simple. Instead of having to write, for example, F1 equals ma1 for particle 1 and F2 equals ma2 for particle 2, because these accelerations will be different because of different radii, we're going to just have one simple equation, which will be, if I write it up here, this. So this is the rotational analog, the rotational equivalent of F equals ma. So the term on the left is torque, which is force times distance, which is the same concept as moment. Okay, it has the same dimensions, units, it's newtons times meters, is calculated in the same way as force times perpendicular distance from pivot, but it's just that sometimes we use this word torque, T-O-R-Q-U-E, instead of the word moment if we're talking about an actual moving system. Okay, I mean the classic example of torque would be somebody might describe the power of a car's engine in terms of the torque it can produce in the wheels. Yeah? How rapidly can a car's engine change the rotational motion of the wheels? That's where the concept of torque is useful. Okay, so we're slowly but surely coming on to the concept of moment of inertia itself. So in torque equals I theta double dot, I, the moment of inertia, plays the same role as mass. I'm not obviously going to try and prove in any sense what torque equals I theta double dot means, but I'm going to give a little sort of toy proof, a kind of illustration of why the concept makes sense. So imagine that, and this is what this paragraph is about, The moment of inertia is the rotational equivalent of mass, just as the force needed to create 1 meter per second squared, that should be, there's a mistake there, 1 meter per second squared of acceleration is proportional to the mass, so the torque needed to create 1 radian per second squared of angular acceleration is also proportional to something. And that something is not mass, but moment of inertia. And to see how that works, imagine a single particle. Yeah? So imagine a single particle. Okay, it's written here, but I'll write it out in notes. Imagine you had a single particle, not a whole body, rotating around a center. So here's a center, let's call it O, and here's a particle, let's call it P. And P is going to travel in a circle around O, so that the radius is R, let's say. Well, we know that F equals ma. So let's write F equals ma. And we also know that if we're talking about torque, instead of force, then torque is Fr, or F times the distance, isn't it? So that should be replaced by, well, rather, if I multiply both sides of the equation by R, I've got this. Yeah, so it's not that F equals ma is not true for a particle P doing this. It clearly is. But we just want to write it in a different way, which doesn't, as it were, which will work for any radius. So that Fr on the left is torque. But on the right, what do we have? We have m times the radius times a. Now, what is a? A is actually r theta double dot. Because v equals r theta dot, so if we differentiate with respect to time, again we get dv by dt, or a equals r d by dt omega or theta dot, which is theta double dot, the angular acceleration. So when we look at this equation, we see we've got the following relationship: torque is equal to mr squared times theta double dot. So that's why we think of the moment of inertia of a single particle rotating about a center at a radius r and having a mass m. We consider that its moment of inertia, which we label I, to be mr squared, and that is the basis of all other moment of inertia calculations. Because after all, if we have a body, a rigid body, remember it must be rigid, of which p is a part, then all we have to do to find the moment of inertia is to add up the moments of inertia of all the particles in the body. So this might be P1, this might be P2, and so on, so that we get a formula something like the sum of the moments of inertia of all the particles in the body. So here I'm summing it over I in the sense that I'm adding up the effect of every one of those particles, P1, P2, and so on. Excuse me. Now, of course, summing is not quite right if we're talking about, let's say, a uniform body. In other words, suppose a body has a uniform density, rho. Then it doesn't make sense to add up individual particles. What we're really doing is integrating, right? Well, this is not really equals, is it? Let's say it's sort of like a sum. And now, what are we summing over? We've got to be a bit careful. The actual process of integration is a process of integration over a whole volume, isn't it? And, you know, each volume element, so it's like the mass of each volume element times the magnitude of the displacement vector from the origin squared, right? It's that kind of idea. Okay, doing it for a three-dimensional object is obviously a bit advanced, and that's the sort of thing you'll do at university. Certainly in many textbooks you're going to find that finding the moment of inertia by a process of integration like that is done for laminas. Now you should remember that lamina is a 2D object, or a two-dimensional object. So let me come back to my notes here. For continuous bodies of 2 or 3 dimensions, such as triangular or rectangular laminas, rods, cubes, spheres, or cones, we can use integration to accurately find the correct value of these sums, these moments of inertia found by adding up the moments of inertia of each particle. However, you will not, see this note in bold here, you will not be expected to find a moment of inertia by integration in the CIE syllabus. By the way, if anybody is watching this and is studying, let's say, Edexcel or some other further maths syllabus, be careful, because as far as I'm aware, some of them do expect the candidate to find moments of inertia by integration. Off the top of my head, I think it's Mechanics Unit 5 in Edexcel, M5, or maybe M4. You'd have to find out for yourself. And certainly in the past, if we go back 10, 15, 20 years, all the further math syllabus is used to expect that you would know how to do that. And that's why you're going to find the method of moment of inertia by integration described in many, if not all, further mechanics textbooks. But let me repeat, if you are taking the CIE syllabus, this is not expected, so don't waste your time reading those sections of the textbook unless you have a lot of free time and you just want to do it for fun. Or maybe you're going to do STEP, or you just think it's an important part of your education. I would totally understand that. So the question then becomes, well, if we're not going to use integration to find moments of inertia of simple objects like spheres, let's say, or circles, circular laminas, how are we going to know what those moments of inertia are? Because we can't just add up the moments of inertia of every particle. So the answer to that question is manyfold or manifold. There are many different methods we're going to use together, and I'm going to make a list of them now and then investigate. So what methods do we have for finding moments of inertia? Number one is use MF10. That means use the formula sheet. There are certain basic standard results for moments of inertia that are just given. And luckily you don't have to memorize them. They are in MF10. So let me find MF10. There it is. So MF10, by the way, does also have results for centers of mass, but today we're focusing on moments of inertia. So we have thin rod, which basically means a straight line, right? A straight line, length 2L, about a perpendicular axis through the center. So already you notice that when we define a moment of inertia, we have to pay attention to not only the position of the center of rotation, the place we're rotating around, but also the orientation. So the moment of inertia of a thin rod about a perpendicular axis through its center, well, I can't show you that on a two-dimensional video, but you just have to imagine if you have a rod, say you take a pencil for example, we're talking about a line perpendicular to that pencil's direction, yeah, and it's also through center. So we always have to define not only the position of the center of rotation, but also the orientation of the axis about which we rotate. Think about that, it should be obvious. So we're given a thin rod, we're given a rectangular lamina. Notice, of course, a rectangle includes a square, and the sides may be A and B there. Then we have a disc, by which they mean a circle in 2 dimensions, or a cylinder, and then we have a sphere and a shell of a sphere. The last two are not used very often, but you know, they're there, so maybe we need them. So the first answer to the question of how to find moments of inertia is use the formula sheet. The second answer, very basic and obvious principle, is addition and subtraction. Well, here I just mean exactly what I was showing you in the diagram on the right, that if we want to find the moment of inertia of a whole solid body, we should add up the moments of inertia of the individual parts of the body. Yeah. Also, equally useful is subtraction, which is really just the reverse process. So you might be confused what I mean by that. So let me give you a simple, very simple example. Let me start by drawing a a circle of some sort. Can I remember how to do this? Select it, and then is it actions? I forget. Change shape to circle. Alright, so let's say that's a circle. We have a circle, and I suppose it's a solid, so that the inside is full, so it's a circular disc. We have a formula for that, but suppose the question asks, what's the moment of inertia of part of this circle? There's the center. Suppose we divide the circle into 3 parts. What is that? 120 degrees there, yeah? And suppose they say, oh, we want you to find the moment of inertia of this third of the circle. So here we can use the fact, actually we're going to use the next method as well as the addition and subtraction method here. I mean, you could try guessing it. I'll tell you right now that the formula for the moment of inertia of a disk of radius r around about a perpendicular axis through its center is 1/2 mr squared. So if we wanted to find the moment of inertia of just this 1/3, I hope you can see it's obvious that the answer must be 1/6 mr squared, because each one of the 3/3 of the circle are equivalent. And therefore, if we add them all together, they must make up 1/2 mr squared. But since each one is equivalent and they have the same moment of inertia, that proves that each 1/3 must have moment of inertia 1/6 mr squared. So I've just realised that's not really subtraction, is it? It is in a sense, in the sense that we're taking 1/2 and we're subtracting 2/3. But really, this example, which is a very good example, is nevertheless really an example more related to the third method I wanted to mention for ways to find moments of inertia. And the third method would be, well, you can call it what you like, it doesn't have a name, but symmetry. The fact that if we have 2 objects which are indistinguishable, or to use a simple word, which are the same in their relationship to the axis of rotation, so those 3 parts of the circle looked the same from the point of view of the axis of rotation, right? Therefore they must have the same moment of inertia. This idea is very important to understand. Without this idea, I can think of quite a few exam questions I've seen that you couldn't solve. Okay, those 3 are kind of basic ones, but then there's other ones which have to be kind of learned, and they are, maybe I'll just write them, save time and write them all at the same time. Theorems. There are 3 theorems. The first is so basic that it often isn't really kind of mentioned, but it's called the Stretch Theorem, which I'll illustrate in a minute. The second one is called the which one first? The parallel, sorry, let's use black. The parallel axis theorem. Parallel axes, plural, theorem. And the third one, similarly, is called the perpendicular. Axes theorem. Okay, so you should review these 3 concepts. They're all very important. Let me briefly show you them in my notes. The Stretch Theorem, which actually it's linked in Wikipedia here, so I think I'll just open these Wikipedia links and show you. It's useful sometimes to review basic concepts on a place like Wikipedia to see a little more detail, if nothing else, just for curiosity's sake. So the Stretch Theorem is the trivial observation that the moment of inertia, I'm reading here, the moment of inertia of a 3D body, which can be formed by stretching a 2D body along the axis of rotation, has the same moment of inertia as the 2D body. Simple example would be the following. If we know that the moment of inertia of a disk about its center, a perpendicular axis through its center, is 1/2 mr squared, and that fact is given, let me remind you, on here, half mr squared for a disk, then the moment of inertia of a cylinder will be the same. And why is that? Because if you take a disk, so take a circle in 2 dimensions, and imagine drawing an axis, a line, cutting through its center, perpendicular to the plane of the disk. Now clearly, if we add another disk with the axis going through the center again, and then another disk, let me draw this in case it's not obvious. Let me draw it out. So if we imagine, and you sort of have to imagine the third dimension here. So I'm drawing a disk side on, and I'm drawing, a vertical axis through its center. There's its center, so cutting through its center. Obviously, if we add another disk, that is terrible, isn't it? If we add another disk, which has, let's say, the same radius and the same mass, that's important. The mass is important, yeah. They'll have the same moments of inertia, so if we add them together, it will just be like 2 versions of the same thing. So it will have the same moment of inertia as a function of mass, right? Suppose the first one has mass m, the second one has mass m. Each one has moment of inertia half mr squared, where r is the radius. So the total moment of inertia is mr squared, which is a half 2m r squared, because 2m is actually the mass of the combined body of both disks together. Now if we add an infinite number of such disks, or you know what I mean, make it continuous, just keep adding disk, 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 what we're making is a cylinder, isn't it? If we keep making lots and lots of these disks, we're making a cylinder. So we can see in a very obvious way that what we've done is taken a disk and stretched it into the third dimension, forming a cylinder. We're not changing the formula for the moment of inertia by doing that. Of course, the mass is changing depending on the density, but the formula for the moment of inertia as a function of the mass is not changing at all. So that's what the stretch theorem says. And another very useful way of applying the stretch theorem would be like this. If you had, which way around shall I do this? If you had a rod, length 2L, so that's L, and there's a perpendicular axis. Now we know according to the formula sheet that 1/3 ml squared is the moment of inertia of this rod, which should be a straight line, about this axis. If we now stretch the rod in a direction parallel to the axis, that's a key point. You see you notice here that I was stretching my disks in a direction parallel to the axis. So if I stretch this in a direction parallel to the axis, what I form is a rectangle. And this rectangle will have the same moment of inertia about that axis as the rod had itself. And so that concept, the stretch theorem, helps us to see, and that's something I leave as an exercise for you to think about. It helps us to see why a rectangular lamina of sides 2a and 2b must have moment of inertia 1/3 ma squared plus b squared. Well, anyway, there's a little bit more to that. Now the other 2 theorems, I did open the Wikipedia pages, didn't I? I don't know if this is really very useful. The parallel axis theorem, here it is, if you can see it, is basically written like that. So IZ equals ICM plus MR squared. That's actually quite a good way to write it, because what that's saying is that if we know ICM, which is the moment of inertia of the object about an axis passing through its center of mass, very important, do not forget, the parallel axis theorem can only be applied if the starting moment of inertia is the one through the center of mass, as in the diagram here. C is the center of mass. So if we have the I through this axis Z through the center of mass, to find the moment of inertia about another axis parallel to that axis, hence parallel axis theorem, but which is at a distance d away, we just simply have to add the mass times the distance squared. We're going to see a couple of examples of that in the exam questions in a minute. So proof of this theorem, if I remember correctly, is not very difficult. You can review that at your leisure. It probably will be in the book as well, but there's no time for that in this video. and you don't need to use the proof in the exam questions. Now, the perpendicular axis theorem, also very useful. I think I've given an example here, yeah, is saying that if we have two perpendicular axes and we know the moments of inertia about those two axes, so let's look at this diagram. Here's some square or something. If we know the moment of inertia of the square about y, and we know the moment of inertia of the square about x, so these are two axes forming a plane, which in this case the plane is the square is in that plane. Do you see? Think of x and y as a graph, just a flat 2D surface. Then the moment of inertia about the axis which is perpendicular to both of those, so imagine a z-axis coming out of the screen, yeah, because that axis is perpendicular to y and x, then you can find that moment of inertia simply by adding the two moments of inertia about x and y, and that's called the perpendicular axis theorem, which is given here. Actually, there's very few notes here. Anyway, that's the theorem. So these two axes are two theorems are very useful. Especially, I think the parallel axis theorem is used very, very often in CIE questions. Perpendicular less so, but you definitely need to know it. Okay. As I mentioned here, very often you will be able to make use of the theorem by combining it with some symmetry of the body. So notice here the axis y and the axis x are equivalent. So by the symmetry of this square you can see that ix and iy will be the same thing. So actually iz will be equal to 2ix. Okay, I think we now have done all the theory. There are some other things about how we combine moment of inertia with equations of motion, but I'll illustrate that as I go through these two questions. Okay, I was just a slight pause there because I was trying to find another way to configure the screen to make this more effective, but it didn't really work, so I'll just do it in a normal way. This question is from summer 2010. It's actually the final question at the end of the paper, so it's going to be a little difficult in theory, although actually this one was pretty easy. Now, obviously, that's the diagram. Let me put the whole question on the screen as best I can. There it is. So obviously that lets you, if you for any reason want to do it this way, you can pause the video right now, read the question, and do it yourself first if you want to. Okay, so now I'll continue. The question has three parts, so we'll break it down like that. And I've actually already done the questions. It's slightly different from my other videos. I'm not going to do it in real time because I don't feel very comfortable with this pen, and it's all a bit difficult. So just as an experiment, I've done it the other way. I did it in advance, and we'll just sort of scroll through, and I'll make any additional notes that might be useful. So let's go to the first part of my answer. So examples. Here's the diagram, and what we're asked to do first is to find the moment of inertia of this system. So the system is described. You have to read it very carefully. Let me emphasize how easy it is to go wrong in doing these kind of calculations, because it's like there's many little facts you need to remember as you do the arithmetic, do the adding and multiplying and subtracting. And I advise you to do this kind of thing slowly, because if you go wrong it can be really rather annoying. I find that nowadays I don't really go wrong very often, but when I first started doing these questions I would constantly make silly mistakes involving the wrong mass or the wrong length, or forgetting to square a number. These things happen all the time. So when we read the question, it's at the bottom there, we notice, for example, the masses of the various parts of the system are different. Certain lengths are different, and also, maybe the most important of all, don't forget to read what is the axis. Remember, the axis is defined in two ways. It's defined by its position on the diagram. Here its position is at A, not at O. And it's also defined by its orientation. Here the axis is perpendicular to the plane of the wheel. You know, not very often, but by no means always, very often the axis will be perpendicular to the plane of the diagram you're looking at. Okay, so we know where the axis is, and we're being asked to find the moment of inertia. So, you know, you need a strategy. Sometimes it's not completely obvious, sometimes, what the right set of steps is to find the moment of inertia. We've got these methods that we mentioned at the beginning. Use standard results, add or subtract, use symmetry, and use parallel and perpendicular axis theorems. So we've got all these tools in our toolkit, but we need to decide which ones to use. So my strategy here was to find the moment of inertia about O first. Now, why is that a good idea? Well, clearly the symmetry of the diagram is such that finding the moment of inertia about O is going to be quite easy. Once we've found the moment of inertia about O, what do we do next? So that's a question for you to answer. If I find the moment of inertia about O, how can I then easily find the moment of inertia about A? Well, the answer is we use the parallel axis theorem. Because if we find the moment of inertia about O, we know that O is the center of mass of the system. Therefore, the parallel axis theorem may be applied using IA equals IO plus the mass of the system times the distance AO. Okay, so that's the whole strategy, but the first step is to find IO, and the way to do that is to find the moment of inertia of each part of the system. So the first step I took was to find the moment of inertia of one single rod, such as OB. Using the standard result, I know its moment of inertia, the moment of inertia of OB about this point, according to MF10, is 1/3 MA squared, where M is the mass of the rod. That's down here. Each of mass M. OB has mass M. So the moment of inertia of OB about that point is 1/3 MA squared. Then I use the parallel axis theorem to find the moment of inertia of OB about O. So that's here. I've added this from MF10, this using parallel axis theorem to get 4 MA squared over 3. That's the moment of inertia of OB about O. So the moment of inertia of the three rods, OA, OB, and OC, by symmetry, they're all the same, must be 3 times that, which is 4 MA squared. Now, the central ring, actually it's not a ring, let me correct that. It's a disk, not a ring, because it's solid. The moment of inertia of the central disk, again I use MF10, it tells me 1/2 times M times A squared, but notice here, of course, the mass of the disk is 4M, so I must use 4M in place of M here. That would be a typical mistake to write 1/2 MA squared, which is wrong because the mass is 4M. So we get 2 MA squared for the moment of inertia of the disk about O. The moment of inertia of the ring is an easy one because a ring, it just consists of a set of particles, all of which are at the same distance from the axis, if the axis is at the center. So you simply have to do m times the distance squared. Now the distance is not a, the distance is 2a, so we need to take the square of the distance 2a, getting 4ma squared. So now if we add together these three, 4ma squared, 2ma squared, 4ma squared, we get 10ma squared, and that is the moment of inertia of the whole system about an axis through O perpendicular to the plane of the object. That was using addition and symmetry, and also parallel axis theorem, of course. Now we use parallel axis theorem again, because now we know the moment of inertia of the whole system about O. We just simply have to add the mass of the whole system. Again, be very careful, the mass of the whole system is not m, but it is 8m, because it is 4m plus the mass of the ring, m, plus 3 times m, so it's 8m, times the distance of O from A squared, so that's 2a squared, that's 4 times 8, 32 ma squared, plus the original 10 ma squared, giving us the final answer of 42 ma squared, which was what was required. So let me repeat, it's not very difficult as long as you've got used to using the parallel axis theorem once or twice, but you must be very, very careful. Now, some students may have chosen to do this in a different way, for example, taking the moments of inertia of each part of the system about A directly. That would require using, well, let me show specifically why that would be a bad idea, although it would work. It would be a bad idea because if we use this as our center point, we're going to have to find the moment of inertia of the rod OB about A. And that will be a little bit annoying because you know the moment of inertia of OB about its center, but then you somehow have to find the distance from that center to A using the parallel axis theorem, which is an extra piece of geometry that I don't want to do. And then obviously OC will be the same, but OA will be different, and then we'll have to use the parallel axis theorem again for the disk and use the parallel axis theorem again for the ring. So it's going to be, I would say, about twice as much calculation doing it that way. So do think about the most efficient way of doing this kind of calculation. That helps a lot. Right, next part of the question is as follows. The axis through A is horizontal. I've circled this. Pay attention to 3D configuration. You must understand, if the question is going to ask something about motion, what that motion is. Is that motion in a horizontal plane, or is it in a vertical plane, or something else? Well, it will never be something else. Here the motion is actually in a vertical plane, because if the axis through A is horizontal, imagine the axis here coming out of the screen and this whole system falling clockwise around that pivot, so falling under gravity. So this is a vertical setup. The wheel rotates freely about the axis. That means that there is no friction to worry about there. The wheel is released from rest with O above the level of A and AO making an angle of 30 degrees with a horizontal. So I've drawn that here. I hope you can see that diagram. The distance from A to O is 2A. The angle that OA makes with the horizontal is 30 degrees. So this is actually pretty simple if you know what to do. Now, one question you always have to ask yourself is this. When there is motion, whether it be rotational or linear, is the acceleration constant? Or equivalently, is the angular acceleration constant? To answer that, you have to know what causes the angular acceleration. Well, what is causing the angular acceleration is, of course, the weight of the system, which is actually 8 mg, isn't it? Which will act through its center of mass. You can always assume that the weight acts through the center of mass of any object. So that weight, that single force acting on the object, acts at that point. As the object rotates, that line OA will rotate, and the perpendicular distance of that fixed force 8 mg from the pivot at A will change, and that means the torque, because remember torque is force times distance, will also change. And if the torque changes while the moment of inertia stays the same, then clearly the angular acceleration will change. So what I do not want to do here is I do not want to try and use an equation like torque equals I theta double dot, and then try and work out maybe something like the final velocity squared equals the initial angular velocity squared plus 2 times the angular acceleration times the angular distance. Right, this final and initial. This equation is correct if and only if the angular acceleration here is constant. By the way, if you've never seen that equation, please do review those notes that I showed you at the beginning of the question. Well, basically you should already know that if you've studied rotational motion. But yeah, review it if you need to. Now that we cannot use that equation because this thing here is not constant. Now, I'm not absolutely guaranteeing that you can't get the right answer by using that method, but even if you get the right answer, please be aware that it is not correct to use that method. So instead of using a method based on a constant acceleration or constant angular acceleration, we must use a method based on energy. Now, the method based on energy is exactly the same as one would use for linear motion. Delta change in kinetic energy is equal and opposite to change in gravitational potential energy, since there is no energy lost to friction and there is no work done by any external forces. That should all be very clear to you from earlier mechanics study, M1 in particular. Now, the only thing you might not know is what is the formula for the change in kinetic energy, and the answer is half I theta dot squared. And I hope you notice you don't even need to try and remember this, because it's exactly the same as this, except in the rotational form. So V is replaced by theta dot, M is replaced by I, which is kind of what we were talking about at the beginning of the video, that the moment of inertia is the rotational analog of mass. So, on the left-hand side, we're going to put half I theta dot squared. I we just calculated in part 1. There it is up there. So we replace that here. And half times that times theta dot squared will be equal to the change in gravitational potential energy. And that's pretty easy to work out, because the height of OA from the horizontal, so how much energy we've lost going from here down to the horizontal, will be the mass, 8m times g times the height, which is 2a sine theta. So we get this long equation, and the only unknown is theta dot squared. Well, we assume that a is just a variable, so that is kept in the final answer. The final answer is 8g over 21a square root. You can replace g with 10 if you want. Yeah. So, as you may or may not know, they very often let the final answer include the radius as a kind of variable. Okay, so that's correct, although you can write it in different forms. So, final part: when AO is horizontal and the disc becomes detached from the wheel. So, what does that mean? It just means, looking at the diagram, that this shaded portion, this disc, will disappear. So when that O reaches the horizontal line, the disc becomes detached from the wheel. Find the angle that AO makes with the horizontal when the wheel first comes to instantaneous rest. So again, here I'm a bit hampered because I can't sort of show you a physical dynamic representation, but you have to imagine that actually exactly as this diagram, we have to imagine that the system has fallen a bit, and we're now in exactly this position with OA horizontal. There's OA horizontal there, if you can see my mouse. At that point, we are now travelling with an angular velocity, which we've just calculated here, 8g over 21a square root. So now remember, there's no friction. So what will happen? The disk disappears. What does that change? Well, if the disk disappears, then this part, well, let's say part of the moment of inertia disappears. So we get a lower moment of inertia, and we have a fixed starting angular velocity with OA horizontal. Now I'm going to show you a very short calculation to get the right answer here. And I guess I'm going to leave it as an exercise for you to try and understand why this calculation is correct. The first step, let's subtract the moment of inertia of the disk, so we get the new moment of inertia without the disk. So to do that, we have to subtract not just half times the mass of the disk times a squared, but we mustn't forget to add the parallel axis theorem part, which is plus the mass of the disk times the distance of the disk from a squared, which is 2a all squared, which is 4a squared. So I've got here 2 plus 16, or 18ma squared. That is the moment of inertia of the disk about the axis through a. Subtract that from the 42 that we previously had, excuse me, and we get 24ma squared. So that's, I've put I dash, that's the new new moment of inertia. Now the height above the horizontal, see if you can understand this, will be found by equating half times that, so just to see the connections here, half times that moment of inertia there times theta dot squared calculated in the previous part, which was the square of the starting angular speed. If we equate that to the mass of the ring plus the rods times g times h, the h we get will be 24 over 21a. And if we equate that to 2a sine theta, so it will actually look something like this: 2a theta, a will be there and o will be there. Yeah, this motion here, we will immediately get the right angle. Sine theta equals 12 over 21. You can work that out. It's something like 34 degrees. Okay, so I'm not going to say any more about that, although I admit I could. The problem, of course, is time is a bit limited, and I think most people can work out from that picture that I've just drawn what my calculation was. Okay, so briefly, time's a bit short, but here's one more question, and this is from Winter 2004. I think I've got it here or something. Oh, that's the answer, sorry. Yeah. So the question is, again, it's a bit of a long one. Let's look at the first part. Here's the first part. If you like, you can stop the video and try and do it yourself. It's actually a very good exercise, although it's not very difficult. I'm sorry, actually, this first part is quite basic. It's the second part that's a good exercise. So this first part asks a very simple question. It says, if we have a square of side 2a formed by just joining together four triangles, prove that the moment of inertia of each triangle is 2/3 ma squared if each triangle has mass m. Here I'm almost just making notes because I think it's very simple. Well, we know that the moment of inertia of a square is equal to 2/3 ma squared if capital M is the mass of the square. Do we know that? Why do we know that? Well, basically we know it from MF10, because MF10 tells us the moment of inertia of a rectangular lamina is 3rd ma squared plus b squared, where a and b are the half sides of the rectangle. So if they're both the same, then we just get 2a squared, so we get 2/3 ma squared. So that should be obvious. And if each triangle has the same moment of inertia, why does each triangle have the same moment of inertia about O? Well, we discussed this at the beginning, right? It's just symmetry. Each of those four triangles is exactly equivalent with respect to that axis, so they almost have the same moment of inertia about O, and the mass of the square is equal to 4 times the mass of the triangle, so the moment of inertia of the square is equal to 4 times the moment of inertia of the triangle. That's just addition, yeah? We add together the four triangles, we get the square. So the moment of inertia of the triangle about O is 2/3 ma squared. Now, of course, this formula, 2/3 ma squared, should use the pen really. The moment of inertia of this formula is the same as this formula, and that again should be totally obvious to you after a moment or two of reflection. But this is just writing a bit more detail. So you can think about exactly how to write it, but certainly you should refer to the standard formula for the rectangular lamina, and you should in some way state that each triangle has the same moment of inertia. I think that's probably enough to get the marks. Arguable, but that's not really what I'm here for. The second part is a bit more interesting. Let me show it to you in case you do want to try and do it yourself. I'm talking about this part here. So there's the new diagram and the new question. Another such triangle with vertex V is now attached to one side of the square. Find the moment of inertia of the combined lamina about an axis L through V perpendicular to its plane. So if you want to, give that a try. And I'll continue now. So again, strategy, how do we do this? There's the diagram. The axis will be through V and again coming out of the screen. Well, my strategy is as follows. First, I'm going to use the parallel axis theorem for the square, because I already know, well, from MF10 I know the formula for the moment of inertia of the square about its centre, and then I just have to add the distance from O to V, squared, or m times the distance from O to V squared, to give the moment of inertia of the square about V. And then I can use what we observed in the first part of the question to add on the moment of inertia of the extra triangle about V. So you see, I mean, I don't know if you might have tried a different method, but it seems quite obvious that that's the simplest method to get the answer. At least it seems that way to me. So notice here a little point about notation. In the more complicated questions on moment of inertia, I would recommend that you follow this notation. Although it's not really standard, it's just something that I've tended to use, which is to annotate, when you write I for moment of inertia, annotate with both the object and the axis. Because if you've got multiple objects and multiple axes, it's very easy to start getting confused about which moment of inertia you're calculating. So this calculation is the moment of inertia of the square about the axis through V. So that's step one. So here we're using the parallel axis theorem, and we're taking, first of all, 2/3 times 4m, because that's the mass of the square, 4 times the mass of the triangle, times a squared. So that's from MF10, from the formulas I mean. Now I'm going to add the mass of the square times the distance of the square, or distance of the centre of mass of the square, to V, which is 2a, and that's all squared. So I've got 4 times 4 plus 8 over 3, giving a total of 56 ma squared over 3. Now the moment of inertia of the triangle about V, for this you just use the result of the previous part of the question, 2/3 ma squared, add that to that, you get 58 ma squared over 3. Okay, last part of the question is as follows, and this is a different type of question. It says the axis is horizontal and combined lamina makes small oscillations under gravity about L. So again, if the axis is horizontal, that means that the motion is in a vertical plane, and we're talking about motion under gravity. It doesn't say that the rotation about L is free of resistance or free of friction, but it must be, okay, so you can ignore that. At time t, the angle between VO and the vertical is theta. Write down the equation of motion of the combined lamina and find the approximate period. So this is a standard type of question about approximate SHM, which I think I must have covered in a previous video, at least I hope I did. So how do we do that? Well, remember that the equation of motion for rotation is torque equals I theta double dot, and that's like F equals ma. Now you could write F equals ma, but I think you're going to cause both you and the examiner, a bit of confusion. Really, they're expecting you to treat this as a rotational motion. It's actually, if you think about it, very similar to a pendulum, isn't it? Because if we draw a diagram, we see that if we treat the whole object as concentrated in its centre of mass G, well, you might say, if I treat the whole object as one point, then I'm ignoring the effect that moment of inertia is trying to calculate, right? Moment of inertia is trying to calculate the effect of the distribution of the object around a centre, and the fact that, you know, if there's more weight further out, then it has more effect. That's true, but that's exactly why we calculate the moment of inertia. That gives us a number which represents that fact. So we can use the moment of inertia here in this equation of motion. We can use this I to represent, we can use I to represent the distribution of the mass around the centre of rotation. And meanwhile, to work out the torque, the actual moment if you prefer, we can use the centre of mass. So I've tried to make a note of this here. The torque is provided by the weight acting through the centre of mass of the combined object. Now the trick here is that we have to find that centre of mass. You should already know how to do this. Certainly when you studied rigid bodies in equilibrium, you should in some cases have had to work out the centre of mass of a combined system. Now the centre of mass of this system is going to be somewhere, actually I have no idea, it's going to be somewhere like here, let's say. Well, that's probably too high up. It's somewhere certainly between O and V, isn't it? Just by an axis of symmetry, that's trivial. The question is, where exactly is it along that line? So in order to do this, we have to combine the centre of mass of the triangle with the centre of mass of the square. Now the centre of mass of the square is obvious, it's at O, but where is the centre of mass of the triangle? Well, again, we refer to MF10. If you don't remember, you should remember really, but the centre of mass of a triangular lamina is 2/3 along the median from the vertex. That means here the median from the vertex, so here the vertex is V, so the median from V is that line there. So 2/3 of the distance from V to, let's call this X, 2/3 of Vx is the distance of, let's say, G1, the centre of mass of the triangle. So to find the combined centre of mass, we have to find the weighted average of these distances. This distance here and this distance all the way down to there. The distance from V to O is more important because 4/5 of the mass is concentrated at O, whereas only 1/5 of the mass is concentrated at G. You see why? Because we have 1, 2, 3, 4 triangles here, 1 here, so 4/5 of the mass is concentrated at O, 1/5 is concentrated at let's call it G1. So let's write down that weighted average. If we take the triangle, we have a distance 2/3 A from V to G1. That's that distance there, and that's multiplied by 1 in my weighted average because I've only got one triangle applied to that centre of mass. And then there's VO, which is at distance O is at a distance 2A if you think about it from V. So that's VO. 1 plus 1 is VO is 2, so it's 2A away, and that's multiplied by 4 in the weighted average, and the whole thing is divided by 5, and that gives us the distance from V to G. So why did we need to calculate that? Just to recap, that allows us to calculate, if we look at this diagram, the turning effect of the weight of the whole system. The whole system has a weight of 5 mg, and that weight must be multiplied by the perpendicular distance of the line of action of the weight from the pivot at V. So that means we need to do Vg times the sine of theta to get d. So the torque finally is equal to the weight there, 5 mg, times Vg, which is 26A over 15, we just worked it out, times sine theta. So that's the torque. And that must be equal to I theta double dot. I we've already worked out, that's 58 ma squared over 3, and then theta double dot is the angular acceleration. So rearranging that whole equation to give an equation in theta double dot gives us the equation theta double dot equals 26 over 58 g over a sine theta. And this is approximately equal to 26 over 58 g over a theta if theta is small. And finally, we observe this is exactly of the form x double dot equals minus omega squared x, or theta double dot equals minus omega squared theta. So this has the form of a simple harmonic motion whose period is 2 pi over omega. And we can see from the equation that omega... actually I always forget to put minus here. Actually this is a minus because the reason is that the torque is tending to make the theta smaller. You can see that the effect of the weight is to pull g that way, which reduces theta, so actually there's a negative sign in the equation of motion. So we could say the torque is negative, and so there's a negative sign here. So 2 pi over omega is to 2 pi over that number, which you can easily work out, 2 pi root 58 over 26g, simplifying as much as possible, that's 2 pi root 29 over 13 a over g. Okay, so that's the final answer for the period. So I hope you found that useful. A bit of a long video, but I'll stop there.